Hi, my name is Seth and I'm a senior engineer with Photonics Dynamics. I'm here to talk to you today about optical computing. Traditional electronic computing is pushing very slow electrons through gold and silver and silicon and copper to perform computing tasks. We call most of the things that we use in processors transistors. Now, transistors are made with a whole bunch of things, but they're mostly novel materials that cost a lot and take a lot of work to put together. Photonics Dynamics has come up with a way to address the challenges that are currently facing electronic computing. The industry as it stands is facing global supply issues. There's the possibility of fabrication facilities not being able to get the raw materials that modern semiconductors need. We also have an issue. For example, Ukraine supplies a lot of neon gas to various countries, and it's used in lithography and chip making. Another issue is security. Transistors emit radio frequencies. Electromagnetic frequencies, electromagnetic emissions, are used to exfiltrate data and compromise high security computer systems. Another huge security concern is undersea optical cable landing stations. They're basically data centers that connect us to the rest of the world through optical cables and some really fancy routing. Another problem is energy consumption. Information and communication technology accounts for an estimated total of 4 to 6% of all electricity used globally, excluding TVs in 2020 alone. Another big issue with traditional computing is heat management. Data center power density requirements are going up year after year. With high-performance compute racks, power densities can reach 100 kilowatts per rack. Now, that's on the high side of the spectrum, I'll say. But the question becomes, what do increasing power densities and a shrinking footprint mean for data center cooling? So last year I was at the Open Compute Project Summit, and there were probably 7 or 8 different vendors offering immersion cooling. So they use oils to cool down your computers. So a lot of data centers are turning to immersion cooling so that they can reduce their energy costs for the heat generated by all these electrons moving around. So an issue that I get excited about is the speed limits. We can't make electrons go any faster. They travel at about 1 millimeter per second. The only thing we can do is shrink the distance between transistors. In 2009, MIT professor Scott Aaronson said Moore's Law was going to die basically in 15 years. It's been 15 years. Computers aren't getting faster. We're just throwing more cores at things. So we're parallelizing, which is good, but the chips themselves aren't going to get much faster than they are. So with the death of Moore's Law, big chip makers have been doing some really amazing stuff in parallelization. So they use buffers and memory that's really close to the chip to reduce the amount of time that it takes for the electrons to travel from one spot to another, making it seem a lot faster for you. This is where optical chips can really make a difference. So we have patented technology and we're building greener chips using less materials. That a standard MOSFET has about 5 to 7 layers. And our optical chips have 3. And they don't require electrons to go through them to work. Quantum computing and all optical chips are really the wave of the future and will be the norm for humanity moving forward. We've been limited by the electron long enough, and it's time for us to change the way we do computing. The real benefits of all optical chips are speed and efficiency. If I could offer a high-frequency trader a 1%, a 0.5% advantage over their competitors, if I could offer a data center a 1-2% gain in efficiency, so we have a number of patents. an all optical nibble bus that allows for way higher than multiplexing speeds without the need for multiplexing. We just went patent pending on an all optical NAND gate. And interesting thing about NAND gates, Shimon Shokin and Noam Nissan created a course called NAND to Tetris. In the course, they actually take you through the building blocks, which is the NAND gate. They put those NAND gates together to build a fully functioning computer, all the way to playing your first Tetris game on said computer. So an all-optical computer designed by Photonics Dynamics could operate in the 50 gigahertz range to the terahertz range, which brings me to real-world implementation. I want to see data centers all optical. I want to see our undersea optical cable landing stations all optical. And I'd really like to see my tricorder work at the speed of light. As far as market potential, cloud computing revenue by 2025 is estimated $832 billion. The global photonics market, somewhere around $800 billion. Data centers are always popping up. I think the world's ready for photonics. So now is your chance to invest. We're currently at the development stage. We have a bunch of patents, and we're shooting for market entry so we can capture the majority of market share before everyone else who's working on this gets into it. So we're shooting for long-term growth potential with a company that values high character. Some of the investment opportunities are option 1, $30,000 for a testable NAND gate when they're ready. Option 2, $80,000 for building wafers so that we can test them for different types of structures that we have in the works. Option 3, invest $150,000 so we can get prototyping, reduce our requirement to test materials on wafers and test them in simulation environments and rapid prototyping. Option 4, partner with us for $20 million so we can build a boutique wafer fab and reduce the requirement for us to farm it out. Option 5, partner with us for $400 million so we can build a fab and start focusing on creating purpose-built optical computers for things like telecom, high-frequency trading, RISC-based optical processors, and the like. So join us at the bleeding edge of technology, and let's start this adventure together. Thanks for joining us.